Okay, so I will start today's lecture. I remind you that in the previous lectures, I have started to discuss the science of light, and I have shown that the discoveries about light have led to the emergence at the beginning of the 20th century, the emergence of the theories of relativity and quantum physics. And in the last lecture, I have described the main principles of quantum physics, the superposition principle, the notion of complementarity, the Heisenberg uncertainty relations, and also the fact that the quantum physics is a probabilistic theory, that it can only predict the probability of results when measurements are performed. And I have also shown that these principles, which were first discovered in a rather intuitive or semi-quantitative ways, were given a very solid ground when the mathematical theory developed. And this theory describes the quantum system as a vector evolving in a Hilbert space, in which the coefficients can be complex numbers. And the fact, for instance, so the states are described by vectors, and the physical observables are operators which act on these vectors in the Hilbert space. And the fact the Heisenberg uncertainty relations are related to the fact that observables which do not commute perturb each other. If you make measurement of one observable and then try to measure another one, the results that you have obtained on the first one scrambles the result for the other one. And this is described quantitatively by the Heisenberg uncertainty relations. Today, I would like to discuss a very important category of observables, the angular momentum or the spin. It's important because the spin is a quantity which is related to the magnetic properties of matter. So there is a lot of applications related to the measurement of spins. It is also important at a fundamental level because the spin is a relativistic observable, something which comes, a concept which comes from relativity theory. And so it's really at the foundation, at the basis of our understanding of matter and of physics. So I will talk about, So I will talk about the angular. First, I will start by talking about what is called the orbital angular momentum. The angular momentum is the quantity which measures the quantity of rotation which exists in a body. It is something which is equivalent, which is analogous to the linear momentum. We know that the linear momentum describes the quantity of motion that you have in a body. It's a product of the mass by the velocity. The angular momentum is a cross product. It's a vectorial quantity, which is a cross product of a radial distance from the rotation center by the momentum, R cross P, and it's a vectorial quantity. In classical physics, it's something which is important because, for example, it's a constant of motion in astronomy, but in quantum physics, it takes another importance. The angular momentum, the components of the angular momentum are product of x and p variables which do not commute, which means that the components of the angular momentum do not commute with each other. And this leads to interesting physical properties that I will discuss here. We will see that the spectrum of the angular momentum is measured in units of h bar. In fact, the angular momentum has the same dimension as an action, and it evolves in units of h bar. And this was known already by Bohr because it was the basis of his quantization of the circular motion of the electron around the nucleus. But now we will understand that deeper by going into the modern theory of the angular momentum in physics. What is particularly interesting is that on top of the orbital momentum, elementary particles, the electron or the proton or nuclei in general, have an intrinsic angular momentum. An angular momentum which describes the rotation, an intrinsic rotation of the particle around itself, so to speak. It's analogous, for example, to the diurnal motion of the Earth which rotates around the sun and which also has a rotation around its own axis. But as we will see, it's not a classical variable. It's something which is rooted in relativity and quantum physics. And the properties of the spin are quite different from the properties of a classical angular momentum, as we will see in a moment. We will see that the electron spin, for instance, has only two possible values around any direction. It points either up or down. Its value is h bar over 2 plus h bar over 2 or minus h bar over 2. And so the spin evolves in a Hilbert space which has two dimensions. You can describe any spin quantum state as a superposition of states whose the basis in this Hilbert state can be the spin up and spin down, and any spin will be linear superposition of these two eigenstates. The operators in this two-dimension space are 2 by 2 matrices, and these matrices are called Pauli operators, and we will discuss the properties of these Pauli operators, which are proportional to the spin operator. It is interesting and important because what we say about the spin can be generalized to any system which evolves between two states. And this is in particular the case of what are called the quantum bits or qubits, which are two-level systems which can exist in superposition states, and all the algebra of the Pauli operators will apply to these qubits, and it will be important when we're talking about quantum information. What I want to say also that the spin is very deeply related to statistics. We will see that fermions have a half-integer spins which are a value 1/2 in general, while bosons have an integer spin, 1 or 2 integer values. And we will see that the statistic, whether particles are fermions or boson, is related to the integer, half-integer value of the corresponding spin. And we'll talk also about statistics. And if I have time at the end of the lecture, I would say a few words about Dirac's equation, which is a relativistic equation of the electron. And this is the root of all what I will be saying about the spin. In fact, the spin and the positron, which is the antiparticle of the electron, were all predicted by Dirac from the solution of his famous equation. So let's start with the angular momentum. And I will start with classical, reminding you some classical concepts by taking as an example the motion of the planets around the sun. So the angular momentum of the planet around the sun is a constant, invariant, is a constant of the motion. For example, if the planet has an elliptical motion, when the planet is close to the sun, it goes faster, but the distance to the sun is shorter, and the product of the velocity by the distance and the sine of the angle is a constant. When the planet goes very far away, it goes slower, and the angular momentum remains constant. In fact, the angular momentum, as we will see on the next part of this slide, the angular momentum is proportional to the area which is swept by the radial vector during unit time. When the planet is far from the sun, the angle is rather small, but the triangle is very long, and the area is the same as it is when the planet is close to the sun. In fact, this is known as the second Kepler's law, and this is something which is related, of course, to the fact that the angular momentum in this motion is a constant of the motion. Now, where does it lead us in quantum physics? When you go to quantum physics, the components of this cross product are written here, and they are products of position and momentum quantities which do not commute. And from this expression of Lx, Ly, and Lz, you can easily, as an exercise, establish the commutation rules. And one finds that the commutator of Lx with Ly is equal to I h bar Lz. So the commutator of any two components of this angular momentum is equal to I h bar, the third one, with a plus or minus sign depending upon whether the permutation between x, y, and z is even, like that, x, y, z, or odd, like x, z, y. So we have either plus I h bar or minus I h bar of the third component. Another important point is that these components, they don't commute between themselves, but they commute with the square of the angular momentum, L square, which is Lx square plus Ly square plus Lz square. So the fact that the square of the angular momentum and any component commute together means that you can find a common basis of eigenstates for L square and Lz, for instance. And this is something that we saw last week, and I will discuss this common basis on the next slide. So you see that you have eigenstates, which are labeled by two indices, L, which is related to the value of the square of the angular momentum, and the square of the angular momentum is equal to LL plus 1 h bar squared. In fact, classically, one could think that it would be L square, but in fact, it's quantum calculation shows that it's LL plus 1 times h bar squared, and L being an integer. The orbital angular momentum takes integer values. And the projection of the angular momentum along a given axis, for example, along Z, is equal to M, has an eigenvalue equal to mh bar, M varying between plus L and minus L. In fact, if you want to give a kind of classical picture, the angular momentum is a vector which makes finite discrete angles with the direction Z, and the M value is a projection of this eigenvector on the Z axis. So it's called spatial quantization. The angular momentum is quantized spatially, and this is a very important result of quantum physics. Now, it's also interesting to say a few words about the eigenstates. The eigenstates, that is a wave function. What is a wave function associated to an eigenvalue of L and M? And it is interesting to describe these eigenstates not in Cartesian coordinates, x, y, z, but in spherical coordinates, which are called r, theta, and phi. In fact, theta and phi are like the latitude and the longitude when you want to point a position on Earth. You have two angles, and you have the distance to the center, which is r. So r, theta, and phi are the spherical coordinates, which are, of course, related to x, y, z. But in spherical coordinates, the physics of angular momentum is much simpler. And the eigenstate corresponding to the eigenvalue L and M is just its wave function. It's just a scalar product, as let me take my second. Yeah. You just take the scalar product of psi Lm with r theta phi, and you get the wave function in this basis, which is a product of a function of r, an arbitrary function of r, and the function of theta and phi are called spherical harmonics. And these are functions which are expressed in terms of cosine theta and sine phi, cosine phi. So this is an expression. These are the eigenstates, and I show you on this part of the slide the shape of this spherical harmonic eigenstates. For L equal to 0, you have only one state, and the shape is very simple. It has a spherical symmetry. The wave function associated to a zero angular momentum is called an S state, and it has the same value in any direction. Now, if you go to L equal 1, you have what are called the P states. You have three states, -1, 0, plus 1. Why L0 has a rotational symmetry around the z-axis and has two lobes, a positive and a negative lobe, and it's an elongated orbital which has this kind of shape. And then by linear superposition of m equal plus and -1, you can build the same kind of orbital along the x and y direction. So these are the P states. If you go to L equal 2, you have 5 states. This is a L20, which has the shape of a kind of elongated shape around the z-axis with a donut around it. And you have -1 and -2 plus 1 plus 2, which give other shapes. These are called D states and so on. You have also L equals 3, 4, and so on. And there is no limit to the spectrum of angular momentum values. why I am explaining this? Because it's useful to understand the geometry of the eigenstate of the hydrogen atom. Look at what this non-relativistic quantum physics allows us to do is to find the eigenstate of this Hamiltonian, which represents the motion of an electron, p squared over 2m. This is the kinetic energy, minus e squared over r is the potential energy. This Hamiltonian commutes with L squared and with Lz. This commutation is a quantum analog of the fact that the angular momentum is a constant of motion in classical physics. To be a constant of motion means that you commute with the energy, with the Hamiltonian, which describes the translation in time of physical quantities. And the fact that you have these commutation rules means that you can find a common basis for the energy, the angular momentum, and its projection on an axis. And you can have a complete set of commuting observable, H, L, and M. And I have shown you here the Eigen Equations. So the energy, eigenvalue of the energy is a Bohr formula, minus Rydberg over n squared. So it depends upon the principal quantum number n. And for a given quantum number, you get the values of L and M. L can take all the values 0, 1, 2, up to n minus 1. And for each L value, you have 2L plus 1 value, which is a projection of L on a given axis. And the wave function of the hydrogen electron is shown here. It's a spherical harmonic, which expresses the fact that these are eigenstates of L squared and Lz, plus a radial function, which depend upon n and L. In fact, in the lecture notes, I put just Rn, but in fact, it's Rn and L. And I show on the right side, part of the slide, the well-known spectrum of hydrogen. N equal 1 is the ground state. N equal 2 is the first excited state, which corresponds to L equal 0 and L equal 1. For N equal 3, you can have 0, 1, and 2. For N equal 4, you have 0, 1, 2, and 3, and so on. And so you have more and more states which are degenerate, which have the same energy when you climb the scale of the energy levels in hydrogen. And you can recognize here the transition between the ground state and the N equal 2, L equal 1 state, and N equals 3, and so on. The connection between the ground state and the L equal 1 state in the excited state gives rise to what is called the Lyman lines, the Lyman series of spectral lines. And the connection between the N equal 2 states and all the N states with L larger than 2 gives the Balmer lines. These are famous lines, spectroscopical lines, which were discovered at the end of the 19th century, but which were not understood until quantum physics enabled us to compute the spectrum of hydrogen. Finally, I give you at the bottom the calculation of the degeneracy of an N state. An N state has a degeneracy which is given by the sum of the odd numbers. And if you go in an N state, you have L equals 0, which has only 1 state, L equal 1 has 3 states, N equal 2 has 5 states, and L equal n minus 1 has 2 n minus 1 states. When you sum all this, you find n squared. So in fact, you have a lot of levels which are all degenerate. It's much more rich spectroscopically than what Bohr had said. Bohr, in fact, had only computed the trajectory corresponding to the circular orbit. And here we see that there is, due to this commutation with the angular momentum, you have a lot of energy states in the spectrum of the simplest of all atoms, which is hydrogen. On this slide, I make the connection between angular momentum and rotations. In fact, what I will show you on this slide is that when you have a quantum state which represents, for instance, a particle at point r, theta, and phi, if you apply this operator to it, you transform it into r, theta, and phi plus alpha. In other words, this operator rotates the quantum state by the angle alpha around the z-axis. And what is the form, what is the nature of this operator? It's an exponential of minus I alpha Lz over h bar. So it's the exponential of the angular momentum. And I remind you, in the last lecture, I told you what is a function of an operator. The function of an operator is another operator which has the same eigenspace, that is, the eigenstate of the operator are also eigenstates of the function, and the eigenvalues are obtained by taking the function by applying to this function, a numerical function, to the eigenvalue of the operator. So this operator is the operator which has as eigenvalue E minus Im alpha on the state Lm. And I will show you that this operator describes indeed rotations. This is explained in a few lines on this slide. The first step is to show that in spherical coordinates, Lz is just the h bar over I times the partial derivative with respect to phi. This looks like what I told you last week. The linear momentum P is h bar over I d over Px is h bar over I d over dx. And the angular momentum is h bar over I d over d phi, where phi is the spherical coordinate, the azimuthal spherical coordinate. So how do you demonstrate that? First, you realize that to go from x, y, z to r theta phi, you apply this formula. X is just r sine theta, you project on the xy plane cosine phi, y is r sine theta sine phi, and z is r cosine theta. What is d over d phi? It's of course d over dx times dx over d phi plus d over dy times dy over d phi. Now dx over d phi is just minus y, and dy over d phi is just plus x. So you find this, and this is just xp minus xpy minus ypx, which is the z component of the angular momentum. So you find that indeed the derivation with respect to phi is proportional to Lz. And now this allows us to find a very simple property of the spherical harmonic. Spherical harmonic YLM is an eigenstate of this d over d pi operator with the eigenvalue mh bar. So you have this equation, which shows that YLM is thus proportional to EIM phi. So the phi dependence of the spherical harmonic is just EIM phi. So we know now this. What happens if you apply this operator, which is diagonal in the Lz basis? You just multiply by E minus I alpha m. You multiply this when you apply Rz by E minus I alpha m, and you get the result shown here. You show that what happens, you get this formula, which shows that applying the rotation operator to the wave function here transform phi into phi minus alpha. So we are already almost at the result I want to show you. From this expression, I make a slight change. I take the conjugate of all this. That is, I transform the kate into a bra, the bra into a kate. So I go to the opposite formula. And if I do that, I have to replace Rz alpha by the adjoint, by the Hermitian conjugate. And the Hermitian conjugation of this is just transforming alpha into minus alpha, or I into minus I. So you have here to transform to, if you want to suppress this Hermitian conjugation, you have to change alpha into minus alpha, and then you get the result, which is here. The rotation goes from phi to phi plus alpha. So this rotation operator is obtained here as a rotation around the z-axis. But in fact, the z-axis has nothing particular. You can get a rotation along any direction, which is defined by a unit vector u. You just take E minus I alpha and the projection of L over U, which is the scalar product with L with U. And this is the operator which describes a rotation around any axis by angle alpha. And this is what is one expressed by saying that the angular momentum is a generator of rotation. You take an exponential of the angular momentum and you can compute the operator which performs any rotation you want on the system. On the next slide, I just summarize the result that we obtained here with results that we obtained last week. I remind you that last week I described the operator which describes translation in space. If you want to translate a ket representing a particle at point R, you apply an exponential operator, which is an exponential of the momentum, with here a parameter which is a quantity that you want to translate by. And by applying this to R, you get R plus R naught. So you see that the momentum, the linear momentum, is a generator of translations. And we have also seen that if you apply the operator, the exponential of the position operator, you get a translation in momentum space. This operator brings the state P to P plus P naught, which is translating in momentum space. And you see that the rotation obeys to the same kind of formula. Here, what we have just shown is that this rotation operator, which is the exponential of the angular momentum, rotates the state. And the last transformation, which we discussed last week, and which is also very important and useful, is a translation in time. And the generator of translation in time is the Hamiltonian. If you take the exponential of the Hamiltonian and multiply by delta t, you transform psi of t of psi of t plus delta t. Now, all these operators, the t, r, and u operator here, have a common property. They are what is called unitary operators, because they are adjoint, which are obtained by transforming I into minus I in the exponential, perform the opposite operation, the inverse operation. That is, if you transform alpha into minus alpha, you do the rotation in the opposite sense. It's the same for P and for the time. So these are unitary operators which describe translation in space, time, and rotations. And these are very important operators in the theory of quantum physics. Now I come to the spin. What I have described so far is the orbital momentum, which has a classical counterpart. Now, on top of that, electrons and also nuclei, for instance, the proton, have an intrinsic angular momentum, an angular momentum which describes rotations, so to speak, the rotation of the system around themselves, not rotation around an external center. And this is called the spin. And the spin is like the orbital momentum, is a vector operator which has three components, Sx, Sy, and Sz. And it obeys the same commutation rules as the orbital angular momentum. And I show you this commutation rule. The commutator of two of the spin components is equal to the third one, plus or minus IH bar. And the value of the angular momentum is special. L is equal to 1/2 in this case, which means that M, which goes from plus L to minus L, M can take only the value plus 1/2 or minus 1/2 H bar over 2 or minus H bar over 2. So the spin evolves, the spin of the electron evolves in a two-dimensional Hilbert space. There are only two dimensions. And it means that the electron, if you want to describe completely the electron, it evolves in a Hilbert space, which is a tensor product, the product of the spatial wave function times the spin wave function. And the spin, so in fact, the wave function has two components corresponding to possible spin value plus or minus 1/2. And we'll come back to this in a moment. So the fact that the spin evolves in a two-dimensional space is interesting because it means that all the operators are 2x2 represented by 2x2 matrices, which means that they have 4 possible matrix elements. So the operators belong to a space which has a dimension 4. And this dimension 4 can be expanded over 4 matrices, which are the 3 spin components plus the identity operator. this makes a basis in the Hilbert space, in the operators Hilbert space. And this is what I want to discuss on this slide. So instead of the angular momentum has a dimension. The angular momentum is equal to plus or minus h bar over 2. If you want to have simple matrices, you just write S equal to h bar over 2 times sigma, and then sigma is dimensionless because you have put all the dimension in the parameter h bar over 2. So you get 3 matrices, sigma x, sigma y, and sigma z, which are proportional to Sx, Sy, and Sz, but which are matrices without dimension, whose mathematical expression is very simple. And I have written here the 3 Pauli matrices. Sigma z is very simple. It's the components along the z-axis, and it's clear that if you are in the basis of the spin up and spin down, this matrix is just +1, -1. If you are in the plus state, you have the eigenvalue +1. If you are in the minus state, you have the eigenvalue -1, because h bar over 2 has been factorized outside. Then you have sigma x and sigma y, which are off diagonal. Sigma x has just the 1 and the off diagonal, and sigma y has -i and +i. And I let you, as an exercise, verify that these 3 operators satisfy the commutation rules of the spin, which should be now sigma, the commutator of sigma y with sigma j is equal to 2 times sigma k. Why 2? Because we have the sigma are equal to twice the angular momentum with the definition I have written here. And so you have this factor. So next, a remark, if you take the square of any Pauli operator, you get 1. So the Pauli operators are, in fact, their own inverse. If you multiply them by themselves, you get the unity. So they are unitary, because their square is equal to 1, and they are Hermitian, because you see that they obey the diagonal elements are real, and the off-diagonal elements are complex conjugate of each other. So these are Hermitian and unitary matrices. I show you also another notation which will be useful in the following. In fact, it doesn't matter whether it's a spin or not. If you have a physical system which can evolve only between 2 states, whether it's a spin or, for example, the ground state and one excited state in an atom, then you can describe all the operators with Pauli matrices. And in general, it's useful to use the following language. The plus state, you call it 0, and the minus state, you call it 1. This is a binary notation, and this is a notation which is useful in quantum information. You code a bit information into a 2-state system, and one state you call 0 and the other 1. In fact, you could take the opposite notation, but this is what is usually done. And so you can express all the Pauli matrices in this basis. And I just recall at the end of this slide the eigenvalues and eigenstates. Of course, the 3 Pauli matrices are all the same eigenvalues, +1, -1, plus h bar over 2 minus h bar over 2. And the eigenstates, these are the eigenstate of sigma z. Sigma z acting on 0 gives 0, and sigma z acting on 1 gives -1. So the eigenstates of sigma z in the sigma z basis, by definition, are the states 0 and 1. What are the eigenstates now of sigma x and sigma y? I'll let you do the calculation, but in fact, it's very simple. The eigenstate of sigma x are the linear combination of 0 plus 1 or 0 minus 1. And the eigenstate of sigma y are the linear combination of 0 plus or minus I1. So you can verify this very easily from these relations. And why do we have the 1 over square root of 2? Just to normalize the probability. If you are in the sigma plus, in the plus state along the x direction, it's a linear superposition of the plus state and minus state along the z direction with equal probabilities. So you have a 1 over square root of 2 to normalize the state. So these are very simple relation. And you see immediately from here the uncertainty relations. if you measure a spin along the z-axis, it has a well-defined value. If you measure the spin along the x-axis and you find it in an eigenstate, it will be this state, for instance. But you see this state is a superposition of plus or minus. So if you have a spin which has a well-defined value along the x-axis, if you measure then along the z-axis, you can find plus or minus with equal probabilities. So you have no information about the spin in a direction transverse to the one in which you have the direction in which you have made the first measurement. And this is, again, an expression of uncertainty relation, not on xp, but on sigma x, sigma y, or sigma x, sigma z. What are the properties of these operators? So I summarize that here. The Pauli operators are traceless. It is the trace, the sum of the diagonal matrix element is 0 for the three operators. They're Hermitian and unitary, which is expressed by these relations. The product of two Pauli operators is equal to the third one, multiplied by I h bar plus or minus I h bar. And you can verify this easily. Third property, which is the definition of angular momentum, the commutator of two of them is equal to 2I h bar, 2I, the third one. Another interesting property, if you make the combination sigma x plus or minus I sigma y, you get, and you can verify this very easily, sigma x plus or minus plus I sigma y give you this matrix 0, 1, 0, 0. And this is a matrix which takes the minus spin along OZ and transform it into the plus one. And sigma minus does the opposite. It takes the plus and flip it to minus. So these operators, sigma x plus or minus I sigma y over 2, are the flipping operators, the operators which bring you from one state to the other. And you can write them in this form also if you want, as the joining a ket and a bra in this way. Finally, another interesting property, any operator in this 2 by 2, in this two-dimensional Hilbert space can be written as a linear superposition of the four operators, sigma x, sigma y, sigma z, and the unity operator I. Now, the coefficient for the unity operator is, of course, 1/2. Why? Because the other operators have a trace equal to 0, and an observable has a trace equal to 1, because the sum of the diagonal elements gives a total probability to find any values for this observable. So you need that it to be equal to 1, and the only way to get 1 is to add 1/2 the identity operator. And then you add a combination of the sigma I. And this combination should have real coefficients. Why? Because you want the operator to be Hermitian, the sigma Hermitian, so the P have to be real. If you have a complex P, this operator will not be Hermitian. So in fact, you see that any operator is in fact described by three components, Px, Py, and Pz, which are like the components of a vector. Any operator is in fact represented by a vector with three components. And we will see this in the following. Let's now look at how do you express rotations on the spin. It's exactly the same way as we did for the orbital angular momentum. A rotation operator is just an exponential of the spin operator, which in terms of the sigma matrices is written in this way. It's an exponential of minus I alpha sigma over 2. Why over 2? Because sigma is twice h bar time the spin. So now let's expand this rotation operator, which is an exponential. You can expand the exponential in powers of sigma. So you have the first order term, which is minus I alpha sigma z over 2. You have a second order term, which is proportional to sigma z squared. Then the third order term, which is sigma z cube, and so on. This is a Taylor expansion of an exponential. And now you have the very interesting property that all the even powers of this are just the identity operator. Sigma square, sigma z square, sigma z to the fourth power, sigma z to the sixth power are all identity operator. So you can take all the even powers here, and you find the expansion of cosine alpha over 2 times I. And now the odd powers, sigma z cube, and so on, they're all equal to sigma z, because they are just even powers of sigma z times 1. And so these odd powers are just give the expansion of sine alpha over 2. And you get now that the rotation of a spin takes a very simple form. It's cosine alpha over 2 times I minus I sine alpha over 2 times sigma z. And this is an example of what I said before. Any operator is a linear combination of here I and sigma z with cosine and sine alpha over 2. When you expand this as a 2 by 2 matrix, you find this. You find that this rotation just defays the plus state by minus EI alpha over 2 and the minus state by E plus I alpha over 2. And as an illustration on the right part of the slide, I show the action of this rotation on the state plus along X. I take the state, I take the quantum state, which is the Eigenstate plus along the X direction, and I apply the rotation by angle alpha. So what will happen if you make a pi over 2 rotation? Clearly, you will go from X to Y. So making a rotation of plus X by pi over 2 will bring you in the plus state along the Y direction. This is what you get here. So this is a general expression. You apply the plus part, the plus X state is a linear combination of plus 6 and minus 6. You apply this phase minus I alpha over 2 to the plus part, the plus I alpha over 2 to the minus part. And now let's make alpha equal to pi over 2. What do you get? You get what I have written here. And without surprise, you find that you find something, a state, which is now plus I time minus. This state is a plus state along the Y direction with a phase factor in front, but so you have now the state along Y. So now what will happen if you make a pi rotation? If you make a pi rotation, clearly what you will go from the plus state along X to the minus state along X. And it's what you get here. The pi rotation brings you to the minus state. You go from plus to minus. You just flip the spin along the X direction. The last rotation, which is interesting, is to make a 2 pi rotation. In ordinary space, if you had just an ordinary classical system, if you make a 2 pi rotation, you come back to the initial state. In quantum physics, if you make a 2 pi rotation, what you find is that the spin comes back in the same direction, but it gains a change sign, the quantum state change sign. You have a pi phase shift, EI pi, which is equal to -1. So a 2 pi rotation of the spin changes the sign of the wave function. And this is something which is useful in quantum information science. And you see, for a spin, if you want to retrieve the same spin, you have to make a 4 pi rotation twice. You have to rotate twice to come back to the exact same state. Otherwise, you have this phase shift. On the next slide, I have expressed how you describe the most general rotation. Suppose that you start with a spin along the X direction, along the Z direction, and that you want to bring it along a direction which corresponds to the angle theta and phi. What you can do is first to rotate by angle theta, bring in the X, in the ZOX plane, and then make a rotation by the angle phi in succession. And this is what I will show you on the right part of the slide. So you have to be careful. You start by making a rotation of angle theta along the, let me see, what is the rotation I have here? yes, you make a rotation around OY of angle theta, which is described by this matrix. I minus sigma I sine theta sigma y. This is a result I obtained on the last slide. And then you multiply by rotation around the z by angle phi, which is given by this matrix. And when you multiply these two matrices, you find this for that matrix and this for that one. And the result is here. So this is a simple exercise that I let you do. And what you find is if you apply this operator to the plus state along z, you get, of course, the plus state along the direction u defined by the angle theta phi. So this product of rotations allows you to write the wave function, the quantum state corresponding to a spin which points in any direction defined by the angle theta phi. It's a linear combination of plus or minus along z with coefficients with amplitudes which depend on theta and phi in this way. You can verify that this state is normalized and that it is a legitimate quantum state. So this brings me to a very simple representation of quantum state and what is called the block sphere. So suppose that you want to define the most general quantum state of a two-level system. That is, you want to find out what is the most general spin pointing in any direction. What you have to do is to choose the direction and to compute the state in this direction. And you see that any direction will give you a point on a sphere, which corresponds to the angle theta and phi, the latitude and longitude on the sphere. And for any point on the sphere, you have a quantum state in the Hilbert space. And you have a one-to-one correspondence between a point on a sphere and a Hilbert space, and the Hilbert space of a two-level system. And this sphere is called the block sphere from the physicists who developed magnetic resonance, because it's a representation which is useful to describe how a spin evolves under the effect of magnetic fields. And I will be using this representation often in the future. So you see here the block sphere. The plus state along the z-axis, or you can call it 0, and the other one along the south pole is called 1. So you see that two orthogonal states are at the antipodes on the sphere. And any point on the sphere corresponds to an eigenstate of the spin pointing along this direction. And you have a one-to-one correspondence between all the possible quantum states and the points on the sphere. So this is a very interesting representation. You see that the eigenstate of sigma z are along the polar axis, and the eigenstate of sigma x and sigma y are on the equator of the sphere. And you see that the plus state along x and the plus state along y are not orthogonal. What is orthogonal is the plus state along x and the minus state along x. Orthogonal states, you have to be careful, orthogonal states, according to the Hilbert space, are antipodes of the sphere, antilinear points of the sphere. 0 and 1 are orthogonal. But if you take the plus x and the plus state along y, if you look at the scalar product, it's not 0. It's 1/2. So this is a block sphere representation. And the last point I would like to make before, 2 or 3 points I would like to make briefly before the break. I would like to introduce a notion of tensor product of Hilbert spaces. The simplest complex combined system you can think of is a system made of two spins. You have two spins, for example, the proton and the spin of the proton and the spin of the electron, and they interact, and you want to describe a quantum state of the combined system of the two. And of course, this combined system will have 4 dimensions. You have 2 dimensions for the first one, 2 dimensions for the second one. And if you want to represent the most general state, you can expand it on a basis, which is the product of, which describe one system in one of the 2 states here, and the other one in one of the 2 states. I call I and J these 2 states, but each of these states has 2 dimensions. So you have a basis of 4 states corresponding to the tensor product of the eigenstate corresponding to the two systems. Now, suppose that if you want to measure an observable of the spin A, that you call O sub A, in fact, if you want to find out what you measure, in fact, in the global system, is an operator which is O acting on A and the identity operator acting on B, because you don't do anything on the B system. So an operator, an observable of part A is just OA times identity on B. And in the same way, an operator acting on B is equal to OB multiplied by identity on the A system. Quite generally, the interaction between the two systems will be described by a product of operators acting on A and B, or a linear superposition of products of operators acting on A and B, and you can write them in this way. And of course, an operator acting on A commutes with an operator acting on B, because they act in different subspace. So in fact, you can just consider them as ordinary numbers as far as multiplication is concerned. So we can now apply this to the case of two spins. And you see immediately, if you take two spins, now you have a basis made of four states. The two spins can be plus, the two can be oriented along OZ in the plus direction, or the two can be oriented in the minus direction, or the first spin can be up and the second down, or the opposite. So you have one basis, which is quite clear, the product of two bases like that. But you can construct other bases by linear superposition. And on the next slide, I give you another example. You can now take the following basis. You keep plus plus and minus minus, but then you add the linear superposition of plus minus and minus plus with a plus sign, and you have also the linear superposition with the minus sign. This is a set of four quantum states which are orthonormal, whose scalar product is 0 if you take two of them. So it's a legitimate basis as the first one. And you see this basis has a very interesting property. These three states are symmetrical by exchange. If you flip, if you change the states from one spin to the other, you get the same result. And the last state is antisymmetrical. If you change the states among the two spins, you change the sign of the wave function. So you have three states which are symmetrical and one state which is antisymmetrical. Now, suppose that you want to measure the total spin, SA plus SB. The operator SA plus SB is obviously symmetrical because SA plus SB is equal to SB plus SA. So if you apply this total spin operator to the three symmetrical states, you will find another symmetrical state. So SA plus SB acting on the symmetrical states is orthogonal to the antisymmetrical state. And in the same way, SA plus SB acting on the antisymmetrical state is orthogonal to the three symmetrical states. In other terms, if you look at the matrix representing SA plus SB in this basis, you have three states here which are symmetrical, which are connected by SA plus SB. And you have one state alone here, which is antisymmetrical and which is not connected by SA plus SB. And so you see that you have made the diagonalization very clearly. You have three states and on one side and one state on the other one. And furthermore, it's obvious now that if you compute sigma Z A plus sigma Z B acting on the two symmetrical states plus or minus minus, you find plus or minus the same. So these states correspond to an angular momentum equal to 1, plus 1 or minus 1. And if you apply the same sigma Z to this symmetrical state, this one, you find 0. So you find that these three states are three states which correspond to an angular momentum equal to 1. There's a plus 1, 0, and minus 1. And on the other hand, if you apply sigma z1 plus sigma z2 on the antisymmetrical state, you find 0. So you see that your division into 3 symmetrical states and 1 antisymmetrical state is also the division between a spin 1 and a spin 0. And what you demonstrate in this way is that by adding 2 spin 1/2, you can either find a spin 1 or find a spin 0. The spin 1 is a triplet. You have 3 states corresponding to spin 1, and the spin 0 is a singlet. You have only 1 linear combination, which gives you a spin 0. So that's another interesting property. Now, to finish this part, I would like to discuss in a more qualitative way some interesting issue about what is really a quantum state. Is it something? Is a quantum state something real, or is a quantum state just some mathematical construction which allows you to make predictions about calculation, which is not real? So what do I mean by real? What is a reality? In classical physics, what I mean by reality, you can say the following thing. Suppose that you have 2 people, Alice and Bob, as usual, 2 people who communicate. Alice has a possibility to build an object, to construct an object. She constructed and she gives it to Bob. And Bob can look at the object under all the faces, can try to reproduce it, to copy it. So this is reality. An object has objective properties that any observer which is given the object can recognize and can use to reconstruct the object. A quantum state is quite different. Suppose that you ask Alice to construct a spin state. The way she can do it is to take a spin and to measure it along any direction. She can put an apparatus which will measure any component of the spin. If she finds a plus value, she will know that her spin has been prepared in this linear superposition. So she has a way to prepare, with an apparatus, she has a way to prepare any combination. Now, when she has prepared that, she gives it to Bob and she asks Bob, tell me what state you have. And the problem is that Bob will be absolutely unable to do that. Because when Bob is given this linear superposition, what can he do? He can decide to measure, if he does not know anything, he can decide to measure one component. He will find plus or minus along this direction. So the only thing he would be sure of is that the spin could not have been orthogonal to the direction in which he measured. But once he has done that, he has destroyed the state because of the fact that he will not be able to measure any component in any other direction because of the non-commutation of the sigma x, sigma y, and sigma z. So there is no way, if you give to anyone a quantum state, for this person to be able to recognize which quantum state it has. The only possibility to do that would be to have a large number of copies. If you give to Bob hundreds of states prepared in the same quantum state, what Bob could do is to divide his sample in 3 parts, measure sigma x on one part, sigma y on the second part, sigma z on the third part, and then he reconstructs the angle theta and phi by statistical measurements, because the probability to get different values are given by the amplitude. So in fact, you see that in this way, a quantum state is an identity card for a system on which you perform repeated measurements on the same copies of the system. So a single quantum state cannot be recognized unless you have a large number of states available. This has a consequence which I show on the next slide. It's impossible to clone, to copy a quantum state. Because if you could copy a quantum state, you would have solved the problem. You are given one quantum state, you make thousands of copies, and you measure on 1/3 of the copies, sigma x, sigma y, and sigma z, and then you construct the state. So quantum physics would be inconsistent if you could clone. And you can find very easily why cloning is impossible. What would a clone machine do? It would be a unitary transformation, which would start. What is a fax machine? You have a sheet of paper and you want to copy it. So you take a blank sheet of paper, you put the text that you want to copy on the machine, and it's reproduced on the blank sheet. the analog in quantum physics would be to start from any linear superposition, for instance, of 0 and 1. This is a blank sheet, 0. And in the end, you get twice the initial quantum state. So you have the original and the copy. But you see that this is inconsistent because due to the linearity of quantum physics, you could also say, okay, if I have a linear combination of 0 and b, I can say that u is applied to the first part. It will give me 0, 0. And u is applied to the second part, and it will transform 1, 0 into 1, 1. And so I would get this form. And you see that the two lines that I've written here are different. In the first line, I have cross terms. In the second line, I don't have cross terms. So the linearity of quantum physics shows that there is something wrong, inconsistent, if I imagine a machine which is able to do that. So it's impossible. And the reason why it's impossible is precisely what I said before. It's a quantum state can only be reconstructed by statistical measurements. And if you could copy, then you could statistically not mean anything. There is another argument which I will discuss later. And we can show that if you could clone, then you could communicate at a distance faster than light. In fact, you could use the property of entanglement combined with cloning to transmit information faster than light signals. And this is inconsistent with relativity theory. So this is interesting. And it's a question. So I have tried to summarize this here. Classically, you can copy. Suppose that if you are clever enough, you can copy any object by just looking at it and reproducing it. In quantum physics, if you are given, for instance, a particle which crosses a slit in a superposition of two states, if you have only one particle, you would be absolutely unable to tell what is the amplitude in one slit to the particle to go in one slit or in the other. So you cannot do that. And one reason you cannot do that is that the cloning is forbidden. So what is the wave function after all? The wave function is very powerful to predict statistical result on a big ensemble of particles. And for a very long time, quantum physics has been used exactly for that. For instance, to understand the properties of matter, you look at a solid or a metal, which is made of billions of particles, and you look at the probabilities to get results if you measure the spins of particles. So you make ensemble measurements. If you look at a gas, which contains billions of atoms also, you make ensemble measurements. And on ensemble measurements, you get very good statistical predictions, but you don't see the strange behavior of quantum physics. You don't see the collapse of the wave function. You don't see entanglement, that we'll discuss next week. You don't see quantum jumps, the fact that the system can go suddenly from one state to the other. So it raises a lot of interesting questions. And these questions were discussed at the beginning of quantum physics. The thought experiments that I described to you last week. In these experiments, the scientists, Bohr, Einstein, Schrödinger, were imagining that it would be possible to manipulate single system, and they tried to get draw some conclusions about that. But then it was very controversial, and a lot of physicists, starting in the 1930s, decided not to worry about interpretation, just to use these laws of quantum physics, the rules, to compute phenomena, to compute the spectrum of atoms and molecules, to compute the properties of metals and of semiconductors, and they were tremendously successful. So their motto was, to the people who still raised question of interpretation, was shut up and calculate. Don't ask yourself this kind of question, it's stupid. And people like Schrödinger believed for a very long time that it would be impossible to work with single particles. And you see this sentence by Schrödinger. He wrote that in 1952. We never experiment with just one electron or one atom or a small molecule. In thought experiments, we sometimes assume we do. This inevitably entails ridiculous consequences. He did not believe in quantum jumps. He did not believe in some of the strange features of the quantum. And what I will show you in the last lectures of this series, that of course, Schrödinger was wrong. Now we can manipulate single quantum systems. we can manipulate single qubits, and you can even hope to be able to do something useful with them. So the wave function has a meaning even at the single particle level. So I will stop here for between 5 and 10 minutes because I have many other things to say in the following. Thank you.